Hello everyone, my name is Anthony Virtuoso and I'm a Principal Engineer with AWS. Today, I'm pleased to announce and introduce you to a new feature of Amazon Athena that enables you to query new sources of data with the same easy-to-use, fully managed SQL interface that you've come to expect when using Athena with S3. Available today, in preview, Amazon Athena's new federated query capabilities allow you to connect Athena to 10 new data sources, or use our open source SDK to connect Athena to your own custom sources and storage formats. Beyond adding new sources of data, Athena federated queries can also take advantage of your own custom UDFs and native support for SageMaker inference. To participate in this preview, simply create an Athena workgroup called Amazon Athena Preview Functionality. Any queries you run from this workgroup in the US East 1, North Virginia region will be able to use this new federated query capability. Later in this presentation, I'll show you how to run such queries and even write your own UDFs and connector to a custom data source. We built Amazon Athena federated queries to help you generate insights and break the data silos that stop you from getting the most out of your data. Let's take a look at a scenario that we see frequently when helping customers with their data lake strategies. As your company's technology estate grows, selecting the best fit for purpose data store for each application, you can end up with useful data siloed into various disjoint systems. We can use this generic e-commerce architecture to illustrate what we mean by data silos. Imagine you were an operations manager responsible for keeping this application running smoothly. By many measures, this estate seems well designed. It separated key responsibilities into different microservices. It used application-specific VPCs to improve its security posture. And each data store has been carefully selected to align with the needs of the specific business function it enables. Let's take a closer look at the database selections. The payment service needs to support a large number of payment transactions. The use case required a right-optimized data store capable of scaling horizontally and offering different storage tiers to enable long-term retention. The team selected HBase running on EMR and backed by S3 for this use case. The order processing service needs to keep track of active orders, providing a low latency interface for downstream systems to get basic details about the status of an order. The team elected to use Redis here because of its low latency read and write capabilities, and because all the data could fit comfortably in memory. The personalization service had to enable the company's global strategy by supporting varying definitions of what a customer or their shipping address might contain. They opted to use DocumentDB to fit their NoSQL use case. The customer-facing e-commerce website itself opted to use Amazon Aurora to meet the read-heavy demands of their product catalog. They valued the scalable read replicas and automated management tools that came with RDS. The operations team selected CloudWatch for their log and metrics needs, since it integrated nicely with the AWS services they were already using elsewhere, and offered convenient APIs for submitting custom application data. The business also established an enterprise data warehouse and associated set of ETLs to offer long-term retention and reporting on the business's KPIs. Redshift was their preferred solution because of its performance in these write once, read many scenarios, and the ability to separate storage and compute via Redshift Spectrum. Lastly, the shipping service needed to normalize shipment processing and tracking for the company's delivery fleet. They opted for DynamoDB because of its ability to meet their tight performance requirements and need for varied schema. Now that we've stepped through this architecture, remember, we're the operations manager. We're in charge of keeping this running smoothly. And it just so happens that our support staff has noticed an increase in the number of customers reporting their orders in a stuck state. With key operational metrics and logs residing in 9 different places, how do you assess the scope of this problem, or even begin to do root cause analysis? With Athena, we can run a federated query to quickly find relevant details, even if we aren't experienced with each of the individual systems that make up this architecture. I've switched to my Athena console now because I want to show you an example query we could run to literally answer that question. How many customer orders are stuck, and is there anything they have in common that might lead us towards a root cause or something that we should investigate further? So I've recreated that architecture that we walked through a moment ago in my AWS account, and I'll walk you through the query I've created using Athena federated query support to do that. So I start my query by querying our CloudWatch logs connector. Specifically, I'm going against the order processor's log group in CloudWatch logs, and I'm querying a special table offered by this connector called the all log streams table. This table is essentially a view over all the log streams in that log group. I'm using some regular expression matching and extraction here to say that I only care about the log lines that are not informational. Right, so presumably this is going to give me all the warnings and errors. I'm doing a little bit more pattern matching here, and I'm saying that I want to extract the order ID from any log lines that match, as well as the log level. Then I'm going to be joining that data against information from our Redis connector, where here I'm going to Redis and getting all the active orders so that I can get just a little bit more information alongside the data that I get from CloudWatch logs. I'm then joining that data against our CMDB connector. And this is a connector that allows you to query your AWS resources as if it were a typical enterprise CMDB. So I can do things like in this case, I'm saying, give me the instance ID, IP address, and state of any of the EC2 instances in this account, so that I can see the connectivity information and state of the EC2 instance that logged each of the log lines that we get from CloudWatch logs. I'm then joining this information with two different tables from DocumentDB, one that's going to give me the customer's contact information, and one that's going to give me their shipping address for the order. Then I'm joining against our shipment details that come from our DynamoDB connector. And I'm grabbing again the order number, the shipment number, the time the shipment was created, and which carrier it used, before finally joining against our payments data using our HBase connector. And in this particular case, I'm interested in what was the status of the payment, what was the last four of the credit card used for the payment, and what clearing network did it use. Okay, so I'm going to go ahead and run this query, and then we'll take a look at what we get back. Okay, and now we have our data back. So we can see we grabbed our order ID from Redis and then joined that against some of the information from DocumentDB about the customer's contact information, and HBase for some of the payment details and status, the shipping details from DynamoDB, and then further over to the side, we can see we got back some information from EC2 about the instance that generated the log lines. And in this particular case, we can actually see that we have two orders that are in a bit of a weird state, and both of those orders were processed by the same EC2 host. So now we have a general idea of what the scope of impact is, right? It seems like there's only two orders impacted. And we have this interesting commonality between those stuck orders, that they both went through the same order processor. So one of our likely next actions is going to be to go and take a deeper look at the logs for that particular host around that time and see if there's something going on there. Or we might even choose to just immediately take that one host out of service while we continue to investigate. So there you have it. We've run a query across 6 or 7 different sources. But what I'd like to do next is actually show you how easy it is to deploy and connect Athena to a new source. Okay, so as you might remember earlier, I mentioned that Athena uses Lambda functions in order to connect to new data sources or your custom UDF. One of the easiest ways for you to deploy one of these connectors and connect Athena to your new source is to go to serverless application repo and use one of the ready-made bundles that the Athena team has authored and published there. So I'm going to go and I'm going to navigate to serverless app repo. I'm going to go to available applications, and I'm going to search for Amazon Athena Federation. And make sure you check this box to show apps that create custom IAM roles, and I'll get more into that in a moment. But this Amazon Athena Federation author name is what you can look for to have confidence that the connector you're about to deploy was authored by the Athena team. Alternatively, you can go to our GitHub repository and build and deploy from source yourself, but this tends to be a bit more convenient. So for this example, I want to deploy our CloudWatch logs connector. So I'm going to go down to Athena CloudWatch connector, and it'll take me to a page where I can see a bit more information about what this connector is going to do. It gives me links to the source code and a description. So I can expand the permissions here. I can see that it's going to need access to read and write data to S3, This is how the connector will get the data to Athena if the response size is too big for Lambda. It's also going to need access to CloudWatch logs. And if I scroll down further, I can see the README with some of the detailed configuration information. And on the right-hand side, some prompts for me to provide that configuration info. So the first thing I need to fill out is the location of a S3 bucket that this connector can use for spilling large responses to Athena. All the data that gets written to that bucket is encrypted using one-time use keys. You can optionally turn the encryption on or off, but we recommend leaving it on, and so it's on by default. In my case, I already have a bucket called Athena Federation Spill. And now we need to specify a catalog name. So catalog name ends up being the name of the Lambda function that will be created, and also the name that I can use to reference this source from inside my Athena queries. So I'm just going to call it CloudWatch. I'm going to leave the encryption turned on. I also get the choice of the Lambda memory limits and Lambda timeout. I'm going to leave those as a default. And lastly, you can specify a spill prefix. So this is going to be a prefix within that spill bucket where any spilled data will be written to make it a bit easier for you to configure lifecycle policies to delete that data after the query is done. I'm going to acknowledge that by deploying this, it's going to grant that Lambda function permission to read from CloudWatch logs. And I'm going to scroll to the bottom and hit deploy. Okay, we can see that our connector has been deployed. So now I'm going to switch back to the Athena console, and we're going to try using our connector in a query. Okay, so let's start with a simple query. This is actually a subset of the query that we ran against our example architecture a couple minutes ago, but I want to dissect this a little bit more so you can get an understanding for what's involved with querying one of these custom sources. So in this case, I'm just doing a select star. I want all the columns from our CloudWatch connector. And the way I'm telling Athena that the table I'm about to query is coming from or is a federated table is with this lambda : CloudWatch. There's also an option that allows you to go and pre-register these federated sources with Athena so that you don't need to use the lambda : prefix for the catalog. But to keep things simple in this demo, I'm using our registrationless option, which allows me to do lambda : and then the name of our lambda function to convey to Athena that it should federate to that particular lambda function for this query. I'm querying our order processor log group and the all log streams table. And let's run our query. And so there you have it. In just a couple of minutes, we went from a couple clicks to deploy to using our connector in a real query. Next, I'd like to talk to you a little bit more about how Athena federated queries work under the hood before going into a tutorial where we'll step by step write a connector from scratch, deploy it, and use it in an actual federated query. During a federated query, Amazon Athena delegates portions of its query planning and distributed execution to Lambda functions that you own and operate. Since these Lambda functions run in your account, they offer you unprecedented levels of control over security, connectivity, and most importantly, the unique ability to customize Amazon Athena with your own code. Our team has written integrations with 10 different SQL and NoSQL databases, including DynamoDB, DocumentDB, MySQL, Postgres, Redshift, Redis, HBase, and CloudWatch. All these connectors, as well as the SDK that you can use to integrate your own custom sources, are open source and available today in our GitHub repository. In a moment, I'll walk you through a tutorial that goes from empty file through writing the code to connect Athena to your custom source in UDF, before ending with running a query that uses our custom source in UDF. But first, I'd like to touch on one of the most common questions I get asked by customers and fellow engineers that I've introduced to these new features. People are always curious how we use Lambda for big data. And while it's true that Lambda functions are limited to a 15-minute runtime and 3 GB of working memory, Athena's execution engine is able to make use of multiple, often concurrent Lambda invocations to pipeline the execution of federated queries, so that your query can run for longer than 15 minutes and make use of more than 3 GB of memory. As part of the validation process that all our technical designs go through, we rewrote Athena's current S3 integration to run on Lambda using the Amazon Athena Query Federation SDK, and then ran several load tests to understand the throughput we could expect when using Lambda in this way. These are not exhaustive figures, but we were able to achieve greater than 100 gigabit per second or 1.5 billion rows per second via Lambda runtime. We expect these figures to improve when this feature reaches general availability. Our usage of Apache Arrow as a standard data interchange format helps reduce the serialization overhead, making it more practical to query data where it lives without the need to manage ETLs. The one caveat to this comes into play for sources that do not support parallel scans. In such cases, your query may be subject to the 15-minute Lambda runtime limit for the table scan portion of your query. We found that most data sources offer at least limited support for parallel scans. Concurrency and other key characteristics of how your federated query executes are all within your control, and Athena provides reasonable default behaviors to get you started. Now I'd like to walk you through a tutorial that will show you how to write your own custom connector for enabling Athena to talk to your data source. In this tutorial, we'll also write a couple user-defined functions. All the material that we're going to go through can be found on our GitHub repository. And in fact, we're going to get started by navigating to that tutorial in our GitHub repo. So I'm going to go to Athena-example. This folder is essentially a pre-made project that will allow you to just fill in a few blanks and be up and running with your own connector and your own UDFs. When you click on that module, you'll be met with a fairly extensive README file that'll talk to you about all the important pieces of a connector, how Athena talks to your connector. But if we scroll down a bit, we'll get to the piece that we're going to really care about, which is how do we build and deploy a connector. The first step, at least in this example, is to create and deploy a Cloud9 instance to use as your development environment. However, any development environment that supports Apache Maven, the AWS CLI, and the AWS SAM build tool should be sufficient. So that'll work on Windows, that'll work on Mac, that'll work on most flavors of Linux. I've already gone ahead and set up a Cloud9 instance to show you how we're going to walk through the tutorial. I've also already done step 2, which is to grab a copy of this GitHub repo and put it onto my Cloud9 instance. So we're going to pick up with step 3, which is installing the prerequisites for the development environment. In this particular case, in our GitHub repository, we provide an environment prep tool that'll work for most flavors of Amazon Linux. If you look at the file, you'll probably be able to adapt it for Mac and other flavors of Linux as well. So I'm going to switch my window back over to my Cloud9 instance, and we're going to go ahead and run this environment prep tool. So I just ran the prep tool, and it's asking me if I'm okay with installing Apache Maven, Homebrew, which is how it's going to get an updated copy of the AWS CLI and the AWS SAM build tool. So I'm going to go ahead and tell it yes. It's probably also going to prompt me at least one more time when it updates Homebrew. Okay, so now it's grabbing updated copies of the AWS CLI and the AWS SAM build tool. Cool, and it's updated my environment. So now if I flip back to the tutorial, let's see what our next step is. I've already sourced our profile, so we should be good. Our next step is to actually build the Federation SDK. So we're using a little bit of a modified command here. We're asking Maven to skip running tests, and that's mostly just to speed up this tutorial. For the most part, you should always leave tests enabled. And I'm also going to be redirecting my standard out to a log file. I found that just makes the Cloud9 IDE run this command a bit faster. But in normal practice, you don't necessarily have to do that. So I'm going to make sure I switch directories to the SDK itself. And I'm going to run it. And this command will probably take a few minutes to build for the first time while it grabs all its dependencies from Maven Central Repository. After the first time, it'll end up having all that in its local cache, and it'll be much faster. Okay, and our SDK has built. We got no error messages to screen, so that's a good sign. Let's go to the tutorial and see what our next step is. Okay, it looks like our next step is actually to sit down and start writing the code for our connector. That the very beginning of that actually includes making sure that we have an S3 bucket ready, so that we can upload the sample data and then have a place to publish our connector to for serverless app repo, which comes a bit later. So I'm going to grab the command that it gives me here for creating a new bucket, and I'm going to go ahead and run it on my Cloud9 instance. We're just going to call it Federation Demo 1000. Okay, so now we have our bucket. All right, now the next thing it's asking us to do is to fill in the code in three different files. The first is example metadata handler. This is going to be the class that'll define the functions that Athena will be able to use to get metadata during query planning. Example record handler, which will provide the functions Athena will call to actually read the data for our table. And then lastly, example user-defined function handler, which is where we're going to put in our user-defined functions. All three of these classes are going to end up getting built and packaged into a single Lambda that we're going to deploy. So I'm going to switch back to my Cloud9 environment, and I'm going to walk you through where those files are, what do they really mean and what are they comprised of. All the information that I'm about to walk you through is available on this tutorial higher in the page. Okay, so on my left-hand nav here in Cloud9, I'm going to expand the Athena example folder. I'm going to go into source, main, and then it should auto-expand and show me all the files we're talking about. The first one we want to modify is example metadata handler. So as I mentioned before, example metadata handler ends up providing the pieces of code that Athena is going to delegate certain parts of query planning. I think there are about four or five different functions in here we're going to implement. The way the tutorial is set up is that these classes essentially have working examples commented out. So I'm going to walk you through each of the functions, what the function is used for, and show you how to implement it. So the first metadata operation that Athena is going to expect to be able to delegate to our connector is listing schemas or listing databases. And that's handled by this function called doList schema names. And what we need to do is essentially return a list of schema names, a list of strings from this function. And you can see that in the tutorial, we have a working example commented out. So I'm going to go ahead and uncomment this example where we're adding schema1 to our response. Now, the names, in general, the names that you put here are not going to be important, right? They should be specific to your data source. This tutorial will only work with the names that are there. So if you change it to say schema 10 or something else, you'll run into trouble later. So leave the names of the schemas, tables, and columns as you find them. The next function that we need to implement is doList tables. Similar to list schemas, we need to return a list of tables for the given schema that Athena called us for. So again, I'm going to uncomment the example, or I should say the example solution. And here we're returning a table called table1, in this case for any schema that Athena calls us for. Our next function is a little bit more involved. Athena is going to call this function, getTable, when it wants to get the definition of a table. And by definition, that means what are the columns in the table, what are their types, are there any partition columns that this table has? So let's go ahead and walk through that and take care of the to-dos in this function as well. The first to-do here is for us to define our partition columns. In this particular example, we're saying that our table is defined on year, month, day. If I scroll down a little bit more, I can see that our second to-do is to produce a schema for the table that we've been requested. So I'm going to uncomment this, and then I'm going to walk you through what it means. If you recall earlier, I mentioned that much of our SDK is based on top of Apache Arrow. So Apache Arrow, in addition to offering a byte-compatible serialization protocol, also offers some other utilities for managing things like schema. So here we're using a schema builder to produce an Apache Arrow schema that will tell Athena what are the columns, their types, and even the comments for each column that are part of this table. So you can see that we start off by defining three integer columns, year, month, day. This corresponds to the partition columns we mentioned a few lines above. Then we're adding an account ID column, which is a string. We're adding an encrypted payload column, which is also a string, and I'll talk a little bit more about that column later. And then we're adding a complex column. This column is of type struct and has two child fields. The first child field is an ID that's of type integer, and the second one is a column completed, which is a bit or a Boolean. That presumably tells us whether or not this transaction is completed. Now we get to the metadata portion, the metadata or table properties portion of this schema. So the important thing to remember about the metadata that we're about to talk about is that Athena essentially treats it as opaque information, with one key exception. If Athena finds a piece of metadata on your table whose name matches the name of a column, it will assume that that metadata is the documentation for that column. So that when you run a show table or when you run a describe table command, you'll be able to see documentation for each column. Any other metadata that you apply to your table, Athena will ignore, but will pass along when it calls other parts of your Lambda function. For example, here we're defining a piece of metadata called partition columns, and we're setting it equal to year, comma, month, comma, day. Athena will ignore this and happily pass it along. But that gives us an interesting piece of plumbing for building our connector upon so that we don't have to keep making round trips to our actual meta story. And I'll show you how we're going to use that later. But at this point, we've completed our getTable function. The next function that we have to implement is called getPartitions. And so Athena will call this function for our table, and it will supply us the predicate for the table, or sorry, I should say the predicate for the query, so that we have the opportunity to do some partition pruning. If your table doesn't support partitions, that's not a problem. You simply don't need to implement this method, and the SDK will take care of communicating appropriately to Athena. However, in this example, we're saying that our table is partitioned on year, month, day. So we're going to go ahead and address the single to do in this function, which is for us to generate our partitions for Athena. So I'm going to uncomment it, and I'll walk you through what's happening. Okay. So in this particular function, we're looping over some number of years, some number of months, and some number of days in order to produce the list of possible partitions for our table. Now, obviously, this is a little bit of a contrived example. In the real world, you should be querying your data source to find out what partitions are available. And then for each of the partitions that we've generated, we're using this block writer, which is a utility provided by the Athena Query Federation SDK, to write our partition response to Athena. This utility essentially encapsulates many of the Apache Arrow functionalities that we would need to use to write this response, and gives us a little bit of more of a streamlined interface for writing that response. You can at any time choose to drop down into a more expert mode and just interact with Apache Arrow directly. So essentially what we're saying here is that every time we're going to call write rows for each of the partitions we generate in our loops. And the SDK will provide us a Apache Arrow block and a row number that we should write into. And then we call block set value, and we're giving it the year, the month, and the day, and we're providing it the values that correspond to the partition we're generating. Set value will actually automatically apply some of the query constraints for us, so that if we keep track of the response values, like we're doing here in this matched Boolean, at the end of the call, we know whether or not this partition satisfies any of the query's constraints. If it does, we return 1, indicating that we wrote one valid row into our response. Otherwise, we return 0, telling the SDK that we haven't written anything. And there you have it. We've implemented our getPartition function with partition pruning. Okay, our next function is going to be the last metadata function we need to implement. And this is going to be our second opportunity to control how Athena parallelizes the federated query. Essentially, Athena will call getSplits for every partition that we returned in the previous function call. And that gives us the opportunity to tell Athena how it can split up the read of that partition. In this particular example, we're saying that the partitions can't be further subdivided. And so we're going to be returning a single split for each of the partitions that Athena calls us for. So I'm going to scroll down, and we'll go ahead and address the to-dos. Uncomment it, and then I'll explain it to you. Okay. So Athena will call this function with a batch of partitions, and so we're looping over the partitions that were in the batch call that was made to us. We're extracting the value of year, month, day from the Apache Arrow request object. And then for each partition, we're generating a single split. Now, a split is mostly opaque to Athena, very similar to what I mentioned before about table properties. But there are two pieces of information on each split that Athena does understand. The first one is the spill location. The spill location is essentially the place where the Lambda invocation will write data if the response that it wants to send to Athena is larger than Lambda's maximum allowed response size. This spill location should be something that should be a bucket or S3 location that you own. It should also be unique per split. And so this function, make split location, is provided by the SDK. It takes in the request that you got, and it will produce a unique spill location in that pre-configured S3 bucket that you saw us set when we deployed, say, like the CloudWatch connector earlier. The second piece of information on a split that Athena does understand is the encryption key. And so when that data spills, if you've set an encryption key for the split, Athena knows it should use that encryption key to decrypt any data that's stored at that spill location for the split. Again, this function, make encryption key, is provided by the SDK. Depending on how you configure your Lambda function, this will either leverage KMS to generate a one-time use key for you, or it'll use a local source of randomness to generate a one-time use key. And then we're applying three different properties on the split. These are not fields that Athena will understand. They're there just for us, so that when Athena calls us to read this split, we'll be able to access these properties and know what we're being asked to do. The first property is year, and we're, again, pulling the year from the requested partition. Same goes for month and day. And then we're returning that information. And at this point, we've completed our metadata handler. The next thing that we need to do is implement our record handler. So I'm going to go ahead and open that. And very similar to the metadata handler, there's already going to be a working solution here, but some of the important bits are commented out. In the case of the record handler, we only need to implement one function. That function is read with constraint. And essentially, Athena will call this function when it wants to read a split. The SDK will take care of all the serialization and some of the other boilerplate for us, and gives us a couple useful pieces of information. The first one is a block spiller. This is what we're going to use to write our responses, and it'll automatically spill any responses that are too large to S3. It gives us the request so that we can get access to the split and any other useful information. And it also gives us this last thing here called a query status checker. This is Athena's way of pushing down limit operations into our connector. We're not going to use it in this particular example, but I wanted to call it out since it is a pretty handy optimization. Okay, the first to do here is for us to grab the information we need off the split. So I'm going to uncomment that. And so for this, on the split, we're asking it to give us three different integer properties: year, month, and day. Next, we're going to handle this other to-do, which tells our connector where the example data that we're going to upload later lives. In this case, it's going to be getting that setting from a Lambda environment variable that we will populate when we deploy the connector using serverless app repo. We can see that it's using the year, month, day that we took off of the split to produce an S3 path that it'll then go and grab our sample data from. The next thing that we need to do is set up the row writer that we will use to translate from our source, in this case a CSV and S3, to Apache Arrow, which is the data interchange format that Athena is expecting from the function call. So I'll uncomment it and I will explain each piece of it. Okay, so essentially the Athena Query Federation SDK provides this generated row writer and associated builder that allows us to create a very performant way of doing this translation from source to Apache Arrow. And the way we do that is by defining an extractor for each of the columns that we want to extract from the source and write back to Athena. So this first example here, we're using the builder and telling it, for the year column, here's the piece of code you can use to extract a year for each row. We use this itSet value to convey whether or not the value is null. It's not particularly interesting for simple columns, but it gets more interesting for complex columns. And then we do the same thing for the month, the day, and the encrypted payload column. Then we get to an example that's a little bit more interesting. The account ID column is a little bit of a special column in this example, in that it's a sensitive field. So inside this extractor, we're actually only returning the last 4 digits of the account ID. And you can see here the code where we're doing that. We're checking the length, and then we're taking a substring of it, so that we're essentially masking this field. And now we're going to take care of our last field, which, if you recall, was a struct field called transaction. And this field was comprised of 2 different child fields. So here inside of our extractor, what we're doing is we're building a map that represents our struct. We're setting a value for ID as well as for completed. And then we're using another utility from inside the SDK called blockutils to set a complex value in our result. We provided that map that we just created, as well as a field resolver that knows how to translate from a map into a struct. And then importantly here, we return true since we don't yet support filtering on we don't yet support predicate pushdown on complex types in this example. Okay, so at this point we've essentially handled all the to-dos, but I'm going to walk you through a little bit of the remainder of this anyway. So now that we've finished kind of building all of our extractors, we actually build our generated row writer. Then we loop over each line in the CSV that represents this particular split in S3. We parse the CSV, and then for each of the lines in that CSV, we call our row writer, and we supply it the parsed line. And that's essentially how we end up writing our response. So that takes care of our connector. I'm now going to transition to the user-defined function handler that we need to implement, and we're going to end up implementing two UDFs that we'll then use in Athena with this data source. So again, same as the other two examples from metadata handler and record handler, we're going to look for to-dos in this file, and we're going to address them. So the first UDF that we're going to implement is called extract transaction ID. And essentially what this UDF does is it will extract the transaction ID from the transaction struct. So I'm going to uncomment the solution, and then we will walk through it. Okay, so the first thing we do is some error and edge case checking. If the transaction is null, or if the transaction doesn't have an ID field, we're going to return -1 to say that it's an unknown ID. And then if it is present, we're simply going to return it. Otherwise, if any exception occurs, we're going to return -1 for invalid transaction. And that's it for our first UDF. Our second UDF is called decrypt, and we're going to actually use this to decrypt that encrypted payload column that you saw in the other parts of the example. So in this particular case, what we're going to do is we're going to call get encryption key, which in this particular example is kind of mocked out to return a static key, but normally would probably call something like KMS or whatever else you're using for key management. Then it calls this symmetric decrypt function, which in this particular case just applies a very basic AES decrypt using the payload, which is the column that was inputted to the UDF, and the key that we just retrieved on the prior line. If there's any errors, we say the result is null, just to avoid failing the query. Otherwise, we return the decrypted string. And that's it. We just wrote two UDFs. Okay. So at this point, we've done, I think, everything that the tutorial asked us to do for that step. So I'm going to switch back to the tutorial and see what's next. Okay, so the last thing we need to do as part of preparing our connectors code is upload the sample data to S3. So the sample data, again, comes with the copy of the tutorial that I checked out earlier. I'm just going to grab this command and upload our data. I'll remember to replace my S3 bucket in the command, which was Federation demo 1000. Okay, our data is uploaded. Now let's switch to the tutorial and see what's next. All right, looks like we're ready to package and deploy our connector. And the SDK actually comes with a pretty handy publish tool, which will take care of packaging everything up, running some tests, and then installing it in serverless app repo for us. I'm going to go ahead and copy this command. It looks like we need to substitute in two pieces of information. The first being the S3 bucket that serverless app repo can go get a copy of the code from, and the publish tool will handle putting a copy there. And the second thing being the AWS region that we want to publish into. When we publish this, it's going to be a private application, so nobody else will be able to see it unless we choose to make it public. But the publish tool should prompt you for that. Okay, I'm going to make sure to put in my AWS region. In my case, I'm working in US East 2. I'm also going to substitute in my bucket name that I created earlier, which was Federation Demo 1000. Okay, the tool tells me what it's going to do. It says it's going to build a Maven project. It's going to create a serverless application package using the YAML file provided in the SDK. It's going to upload the connector to the S3 bucket we provided. It's going to check if serverless app repo can access that bucket. If it can't, it'll prompt us to add a bucket policy to enable serverless app repo to read from it. And then lastly, it will publish the connector to serverless app repo. I'm going to go ahead and hit yes. It checked my bucket, and my bucket is indeed lacking the bucket policy, so I hit yes. It shows me the policy and it applies it, and then it starts building our connector. This takes a little while the first time while it downloads dependencies. Okay, so our connector passed testing and was just uploaded to serverless app repo. So next thing we're going to do is we're going to switch over to serverless app repo and we're going to deploy that connector. And then we're going to see what else the tutorial tells us to do. I'm on serverless app repo and I'm viewing my private applications, and I can see the one I just built and deployed. So I'm going to go ahead and click on it. And similar to the other example we did earlier with CloudWatch logs, it's going to ask me a few questions. The first one is, what do I want to call this catalog in Athena, and what do I want to name that Lambda function? So I'm just going to call it example. Second question is, what's the data bucket? Meaning, where can I go get the sample data? So my bucket was called Federation Demo 1000. And I'm going to use the same thing for my spill bucket. And everything else I think I'm going to leave at default. I'm going to leave encryption enabled, and I'm going to leave the Lambda settings the same. I'm going to acknowledge that this is going to create an IAM role to read S3. And if I scroll to the bottom, I should be able to deploy. Okay, and now we can see our connectors deployed. Let's go check the tutorial and see what we should do next. Okay, so the next thing the tutorial would like us to do is to validate our connector. And the reason for this is because one of the most challenging parts of integrating systems is integration testing. So the SDK comes with a validate connector tool that will call your Lambda function and simulate the traffic patterns and calls that Athena would make as part of a query. So I'm going to go ahead and copy this command, and then we're going to have to substitute in the name of our Lambda function. So in my case, I called the Lambda function example. Okay, and it's telling me what it's going to do. It's going to build the Maven project for the validate connector tool if it's not already built, and then it's going to call our Lambda function. So I'm going to hit yes. Okay, and our connector passed validation. We can see at the bottom here our little successfully passed validation message. I think now we're ready to run a query, but let's check what the tutorial would like us to do. Okay, it looks like we are indeed ready to run a query. So I'm going to copy this first example query, which looks like it uses both our UDFs as well. And I'm going to switch to my Athena console. Okay, so I've pasted the sample query in, and now we need to substitute in the name of our Lambda function, and then I'll walk you through what this query is going to do. So my Lambda function was called example, so I'm going to just replace it in the two user-defined function definitions, and then also in my data source definition there. Okay, so what this is doing is on lines 1 and 2, it's defining our extract transaction ID user-defined function, and it's saying that it takes a row or struct as input, and it expects that row or struct to have two fields, ID and completed, and it returns an integer. It's also saying that this particular user-defined function is a Lambda invocation style user-defined function, and the name of the Lambda to use for that invocation is example. It then defines a second function called decrypt, which takes as input a varchar or string and returns a varchar, and again is a Lambda invoke type UDF that's hosted on a Lambda called example. And then we have a select query. In this case, we're selecting the year, month, day, account ID, and then we're selecting the encrypted payload column and passing it to our decrypt UDF. Before taking the transaction column and passing it to our extract transaction ID UDF. And we're saying that this is coming from the Lambda example data source, which maps to our example connector that we just wrote. And then we're filtering on the year, month, and day column. So we're essentially querying just a single partition of this custom table. So I'm going to go ahead and run our query. And you can see that we got some data back. Probably the most interesting parts are that account ID column, right, which we can see is now masked down to just the last 4 digits. Our decrypted payload column, which we can actually read now because we've decrypted it. And then lastly, we've successfully extracted the transaction ID from the struct. Okay, let's go back to the tutorial. And I think there's one more interesting query we can try running. So the tutorial also includes a couple example DDLs we can try. So let's get the query that'll let us describe the schema of our example table. Go ahead and paste that in here and run it. Oh, actually, first I'm going to insert the name of my source, which was example, and then I'll run it. And you can see that we get back the schema information. I can see that it's got an account ID, an encrypted payload, transaction, which is a struct column, and then 3 partition tables. And we're done. So we've written a custom connector. We've written some custom UDFs. We've used the connector and UDF in a query. I've shown you how to deploy one of our ready-made connectors from serverless app repo. And we've talked about how Athena federated queries can help you get at your data even when it might have been siloed in various application stacks. So thanks for spending the time with me to go through these new features.